So here's the guess we would make for the behavior of the solution, or a sketch of the behavior. So I'm going to have some axes, of course, right? And I'm going to try to figure out here what the current is on this axis as a function of time t on this axis. And one of the key things we know is that before t equals 0, the current is 0. So that tells me that if I sketch the current over here, right, I'll draw a thick line for the actual graph on top of my axes. So the current is 0 until I hit this point. And now at time t equals 0, I flip the switch and the current is going to begin to flow. But there's something very interesting about this equation, right? You might think, oh, well, if the current flows and I have a battery E and a resistance R, I've seen many circuits like this. The current should be then just E over R. So you might guess, for instance, that the current would immediately jump up to this value of E over R. But if I did that, there would be something very strange about this system. Notice that the current would be discontinuous. And if I take the slope of that at time t equals 0, if there's a discontinuity, the slope is infinite. But if I had an infinite slope, di dt infinite, that would make the left-hand side of my equation infinity. But if I look at the right-hand side of my equation, there's nothing here that can match infinity. This side can't be infinity. I've got a certain finite voltage for my battery. The current here is just finite. The resistance is finite. So this di dt term has to be finite. And if it's finite, there can't be any discontinuity in the current. So that is not possible for that jump to happen. In fact, what has to happen is that even though we can guess that the current wants to start to increase, it has to be a continuous function. And to be a continuous function, then the current has to come in to 0 like so. So let me make a little note of that. That's a very important lesson, that when we close S, right, when we first do that, there can be no discontinuity because di dt, that time derivative in our equation, has to be finite. So that's interesting. That's good to know. Now, let's see what happens. So initially, the current is going to have to be 0, but then it can start to increase and current can flow through my circuit. Now, if I wait a long time afterwards, take the other limiting case. If I go to long times, eventually I would hope I would reach some kind of steady state, and this circuit would begin to settle down. And when it settles down, we know then things will stop changing. The current now will no longer be changing, and di dt now will become 0. And if this side is 0 when I reach a steady state, then I have 0 equals E minus IR. Well, that equation I can solve. I'll find, putting IR on this side of the equation, IR equals E, where I equals E over R. So in fact, I get this value that we might have been guessing at, but I don't obtain this value for the current initially. I have to wait a long time until my circuit has finally settled down. So there's probably some kind of very familiar, right, looking kind of exponential behavior as I approach this final value here. So we've just learned then 2 key lessons for inductors and limiting cases, just like we had for capacitors. So here are the lessons that we've learned, right? So if I have some inductor circuit, when any switch flips, if I make any sudden changes in my circuit, the current through all of the inductors has to be the same before and after I flip those switches. So I is constant. Well, I don't want to say quite constant. I would say is continuous. So I, the current through any inductors, is continuous. And that really is just a reflection of Faraday's law. remember that that the whole point in an inductor is, and Faraday's law or Lenz's law is that it's going to resist any change in the flux. So if you suddenly try to increase the flux, it's going to produce voltages that try to stop that flux from changing or increasing. So inductors always try to keep the current flowing through them continuous when you flip a switch. But then eventually you will reach steady state. Now, so as we begin then to approach steady state, right? And this then means we're talking about the time goes towards infinity. When you approach that kind of situation, as we've said, when things stop changing, this effective voltage across the inductor then goes to zero. And if it goes to zero, well then of course that just is acting like what it looks like on the diagram. It acts like a simple ideal conductor, which never has any voltage drop across it. It acts just like a wire. And in fact, if we replace this with a wire, then we have a standard battery resistor circuit, and we would get the current exactly correct. So as that happens, then the inductors act like wires. Act like ideal wires. Very good. So those are the key general physical principles that you can use to understand the limiting case behavior that we would expect out of inductor circuits.